Chapters 11 and 12, Estimation of Absolute and Relative Performance, Part 4. This is the last part of the pre-recorded videos on these two chapters. So we had the case of independent sampling in the previous part, and now we are going to consider the common random numbers method, CRN method here. So here we assume that the stream of random numbers used to simulate the two systems are the same. So we are going to use the same stream of random numbers for the two simulation models. Okay, so for each replication R, the estimate on YR1 and YR2, since both have the same random number, so they will be somehow correlated, right? They're not independent anymore. Okay, so the two systems will also have the same number of replications, R1 equals R2 equals R. Okay, so and that's it. So so why we are going to use this approach? Why we are going to have the same stream of random numbers? The reason is this: we want to introduce a positive correlation between YR1 and YR2 through the CRN in order to reduce the variance of mean difference point estimator. So yes, this is the objective. We are going to reduce our error, reduce our variance, and that's the point. So here, since y.1 and y.2 are not independent, then the variance will be this: variance of y bar 1 plus variance of y bar 2 minus 2 times the covariance between y bar 1 and y bar 2. Okay, and then by having this covariance term, we will obtain the variance under the case of CRN, and then we can compare it with the variance under the independent sampling. And as you see here, the variance under CRN is the variance under independent sampling minus a term, and this term is a positive term. So because of that, the variance of CRN will be always less than the variance of the independent sampling. Okay. So here we want to build a confidence interval with 1 minus alpha percent confidence level for theta 1 minus theta 2. Okay, so for each replication, at first we calculate dr, the difference between the two measures. So dr will be yr1 minus yr2. Okay, and then we can calculate the d bar, the average difference between the measures, and then we need to obtain the sample variance of dr and the standard error. So it will be calculated by this equation, and also the standard error for d bar will be this, and here the degrees of freedom will be r minus 1. So now we do have our confidence interval here: d bar plus minus a standard error of d bar, which is st over square root of r, times d half alpha, and nu, which is r minus 1. Okay. We have an example here. It's about the SMP call center. In the current system, they have 7 operators, and they are in 2 categories. So the system is thinking about cross-training the operators in order each operator be able to answer any call. Okay, and then the system thinks that by doing that, they can reduce the number of operators by 1. So they want to see what will be the impact of this change on the system in terms of the average call response time. Okay, so to validate the change in policy, we need to consider these two scenarios. These two somehow comparisons: the current system with 7 operator versus the cross-trained 7 operators. Okay, and the cross-trained 7 operators versus the cross-trained 6 operators. Okay, so So in order to have those comparisons here, we have three uh, three systems: a current system, proposed system with 7 operators, and proposed system with 6 operators. And here we do have the average response time obtained for 10 replications. Now we can calculate the differences between current and the proposed with 7 operators, C minus P7, and the current system and the proposed system with 7 operators and the proposed system with 6 operators, so P7 minus P6. Okay, so here we do have the differences, so we can calculate the confidence interval for the difference. So for the C minus P7, this is uh, the confidence interval. So it will be minus 2.26 and 0.54 minutes. Okay, and for P7 minus P6, we will have minus 7 and again minus 3.049. Okay, so by having this result, I'll upload the Excel file learn, so you'll have the solution over there. And here I'm just analyzing its outcome. So here we do have two confidence intervals. The first one, as you see here, contains 0. So this means that C, the current system, should be equal to P7. So this means that there is no considerably difference between the current system and the proposed system with 7 operators. Okay, but in comparison between the proposed system with 7 operators and 6 operators, as you see here, the confidence interval is all negative, so it lies on the left side of the 0. So this means that theta 1 minus theta 2 is negative, so theta 1 is less than theta 2. So this means that the P7, I mean the average response time in P7 is less than the average response time in P6. So this means that if we reduce the number of operators by 1, then we will increase the average response time, right? So by this criteria, reducing the number of operators by 1 is not a good idea. So we are not going to decrease the number of operators. And since the proposed system P7 equals statistically equals the current system, so this means that we can ignore that change and just stay with the current system. Okay. If we want to have a confidence interval here with a specified precision, so we can follow the same approach that we had before in chapter 11. So here we have an epsilon, which is a desired level of error. So now we can obtain actually how many replications do we need in order to reach that level of precision. For example, in example tool 1, in the previous example, we constructed a 95% confidence interval for the difference between the current system and the proposed system with 7 cross-trained employees, and it was this interval. Okay, so and the number of applications was 10. So the D bar here is minus 0.86, R0, the initial number of applications, is 10, and the variance, the sample variance, is 3.87. Okay, so we can obtain the value of R, the required number of replications, by the equation that we do have here. It will be 238. So this means if we want to reach to a precision level of 0.25, I mean the epsilon 0.25 minutes, then we need to have 238 replications. Okay. The comparison of several system configurations. So here, let's say we do have k alternatives as system designs, and we want to compare the performance measure theta I among the k alternatives. Okay, so the question here is this: what will be the overall confidence level if we build a confidence interval with 1 minus alpha percent confidence level for each theta I? Okay, so here we mean a family-wise error term. Okay, so here we have a method. It's called Bonferroni method or Bonferroni approach for multiple comparisons, and by doing so we will obtain that a confidence level for each comparison in order to have a confidence level in total in the whole for all comparisons. I mean the family-wise error term. Okay, so let's say we consider one of the cases, one of the alternatives as the standard one. Let's say that's theta 1, and then we compare the other systems against this system. So system 2 against system 1, system 3 against system 1, and so on. So theta, we will construct a confidence interval for theta 2 minus theta 1, and then another confidence interval for theta 3 minus theta 1 up to theta k minus theta 1. So as you see here, we will have k minus 1 comparisons, right? So we have k alternatives. We consider one of these ones, let's say theta 1, as the standard one, the base case, and then we will compare the rest with this one. So we'll have k minus 1 comparisons. Okay, so let's say we want to achieve the overall confidence of this. I mean 1 minus alpha percent in the overall confidence, family-wise confidence level for all k minus 1 comparisons. Okay, so in order to reach this confidence interval, we need to have the confidence interval for each comparison with this confidence level. So we need to divide the alpha by k minus 1. By doing that, actually we are somehow widening each confidence interval in order to have that desired confidence level in total for all comparisons. Okay, then so that's for the case that we consider one of the alternatives as the standard one, and then compare the rest with that one. So we do have k minus 1 comparisons. But what if we consider all pairwise comparisons? So in that case, we'll have this number of the comparisons, k times k minus 1 divided by 2. Okay, then so here, same as before, we just need to divide the alpha by this number. So it will be, so this will be the confidence level for each comparison. 1 minus 2 alpha divided by k times k minus 1. Okay, so yeah, and that's it. So here, the concept is this: we are widening the confidence interval for each case in order to have the desired confidence level in total for all comparisons. Okay. Now let's consider the previous example, the SMP call center, and consider those three alternatives: the current system, the proposed system with 7 operators, and the proposed system with 6 operators. Okay, so if we want to analyze this example with Bonferroni approach, so we'll have 3 comparisons. So in total we will have 3 comparisons: theta c minus theta p7, theta c minus theta p6 and theta p7 against theta p6. Okay, so since we do have three comparisons, so we need to divide alpha by 3 for each comparison, for each confidence interval for each comparison, in order to have the 95% confidence level at the end in total for all comparisons. Okay, so you can find the solution of this example in the Excel file. And so here, as you see here, since the confidence level for each comparison is this, then if we, and since they are somehow independent comparisons, so the confidence level at the end will be the first one and the second one and the third one, so we need to multiply the confidence levels. So here is the reason that why we do have the power of 3 here, and that will be the confidence level at the end by having 3 comparison, and it should be greater than or equal to 95%. Okay. So as a discussion, in Banfroni approach, we consider a desired overall confidence level in order to reduce the family-wise error rate. Okay, and in section 12.2.2 in the textbook, you can find an approach to somehow optimize the system configuration. So in Banfroni approach, or before that, we have a limited number of alternatives, and we're just comparing those limited alternatives. But we can actually apply an approach to optimize our quantity. For example, let's say our quantity is the number of employees. So what's the optimal number of employees in that system? We can consider 7, 8, 6, 5 and compare the results in order to find the one, but that's not guaranteed that that solution would be optimal, right? So we can apply a method for optimizing that quantity, and you can find this approach in section 12.2.2, but we are not going to cover this part in our course, so it will be considered as self-reading. And for your project, actually, you can apply the comparison method. If you have just 2 alternatives, or if you have more than 2 alternatives, you can apply the Banfroni method. You don't have to follow the optimization approach, but if you do so, you will get a bonus mark. Okay, and that's it. We are done on chapter 12. Thank you.